So let us now talk about the utility theory of von Neumann and Morgenstern. As I said, it's known that it's not exactly that these are how preferences are built, at least not in many cases. We do employ this model, and many researchers employ this model too, but it's known that sometimes that's not the case. So, for example, this model will assume some sort of independence, which is natural to require, but people are not like that. People do depend on, in their choice, people can depend on something irrelevant, seemingly, because we are people. That's a question for evolutionary biology, why we have those weird irrational tendencies, at least sometimes irrational. So there are those paradoxes of Lie and of Ellsberg that show that these are the von Neumann-Morgenstern theory is not true, but still that's useful, important to know. Actually, the theory which eventually, probably the most famous theory which substituted that, is the prospect theory of Kahneman and Tversky, for which Kahneman got Nobel Prize and Tversky simply had died before that. Of course, otherwise he would also have got the prize. That theory is also, as Kahneman himself writes, not completely ideally characterizes how people behave. So that's a question which is still open. So there is ongoing research how to completely characterize how people behave, but we are going to assume this so-called linear utility theory by von Neumann and Morgenstern. So let us now see a bit what it is. So a lottery, because people often choose between random options, not between only this deterministic one, and a lottery, this is going to be a basic object between which people choose. So a lottery is a distribution of outcomes denoted as a convex combination with weights P of outcomes OI, where on I's are the mutually exclusive outcome from some set O, capital O of outcomes. Now, a convex combination means that the sum of the coefficients is exactly 1 and the weights are positive. So it's basically probability distribution. So I is a distribution of a certain outcome. You can even say all outcomes, simply some outcomes which don't appear, we get the weight of 0. And we denote also the preferences in those curly notation. And now the central theory we're going to use is a theory which allows us to assume that the utilities, the preferences, which in the beginning are given just who prefers what to what, so only comparison, that they can be characterized by a so-called utility function. And that's what we are going to assume. And that's the theorem. So the theorem is complicated. We always assume that assumptions hold, and they're going to usually work with utility functions from the beginning. And the theorem sounds like that. Consider a finite set of outcomes. Remember that's the set O from which outcomes are taken. And preferences, which say exactly who is less or equal in preference over the set of lotteries, so the set of those randomizations of that set of outcomes. And they assume that the preferences are closed under mixing probability. Means that for any p between 0 and 1, if we mix excuse me, it should be not p and q, it should be p and 1 minus p. So if we mix p for any p between 0 and 1, P L1 plus 1 minus P. I just written Q, but I meant 1 minus P. Or for actually, it does not have to be 1 minus P. Any combination of 2 between 0 and 1 such that their sum is at most 1 is also a lottery. So that's what means that it's closed under mixing. Moreover, we assume it's not just a lottery, but we assume that we can enter those coefficients inside the original distribution. So if if one of the lotteries is the sum of pi li, and we take alpha times that plus beta times the other lottery with the coefficients q, then if the final lottery is simply the same from the preference point of view as taking the coefficients alpha pi plus beta qi. So there is this linearity assumption, and then the preference satisfies the axiom. Then the preferences satisfy the axioms, if and only if, we are going to cover the axioms soon, but if and only if there is a utility function, which is what as I've said, what they want. So she said for every outcome there is a real value, such that a certain lottery is preferred to another lottery, if and only if the combination of the utilities of those outcomes with exactly the same weights, here P and P, is at most the combination of the utilities of the outcomes. So in order to say which lottery is preferred, we can simply compare the values, the expected values of the utility function. Now, if it exists and such a utility is unique, up to a positive linear transformation. So if we define such a function, then it's unique up to a positive linear transformation. But again, we are not going to talk about how to find such a function. Often we are usually going to have this function, but it's important just to notice what happens. So again, let us now go into the axioms which are required, which actually are equivalent to having these utility functions. So they're quite natural. As I said, there is a reason that was the first theory. That's very natural to assume that's what people want. Unfortunately, or luckily, probably from the evolutionary point of view, luckily, we are not exactly that simple. So completeness. So for every two outcomes, either one is preferred to the other one, or the other one is preferred to the first one. And now, so it's a complete order transitivity. So if 2 is preferred to 1 and 3 is preferred to 2, then 3 is preferred to 1. Continuity. Then for any chain of 3 outcomes, lotteries, so combinations of outcomes, such that L2 is preferred to L1 and L3 is preferred to L2, and of course then from transitivity to F1, but L3 is preferred to L2. Continuity means that we can exactly find some P between 0 and 1 such that L2 is the combination, the convex combination of P times L1 plus 1 minus P times L2. So if it's between them, we can look at this, we can express this as a convex combination of those lotteries. And independence, which means that if that's exactly what I said, that one of those paradoxes of Beiersberg shows to be wrong. And we know that we are not really independent. But let us first formulate what it is. So that if L2 is preferred to L1, then for any P between 0 and 1, combining any L3 with L1 and the same weights, combining it with the same weights, combining L3 with L2 will not change it. So if I prefer, very roughly an example, if I prefer apples to P and apple to a pear, and you give me, say, okay, I'll give you half an apple and 2 grapes, and compare this with half a pear and 2 grapes. And since I added the same thing with the same weight, the result of the comparison will be exactly the same as the original thing. So if I prefer the apple, then I would also prefer half an apple with 2 grapes to half a pear with 2 grapes. That should be right, but I don't exactly remember the conditions. There was a famous, I think it was the later experiment, not exactly those paradoxes, which is called framing. So it's important how the form of a problem is formulated in order to us to decide what we want. So we can say that we want to go to Berlin, then more than we're going to go to Paris for given prices. But if we are given yet another option, which we definitely won't take, but simply we have another option in the picture, then our preferences can be reversed. Because then we are going to think in a different way. Because we are not, in reality, most people, statistically we, are not exactly optimizing, not always optimizing. So to recapitulate it, consider a finite set of outcomes and preferences which are closed under mixing probability and reducible, which is kind of a linearity requirement. Then these 4 axioms, completeness, transitivity, continuity, and independence, which in my opinion are very natural, are equivalent to having a utility function which expresses preferences. But we are going to always assume that we have this utility function, almost always. But that's kind of the fundamentals of game theory, or even a more fundamental theory on which we are based. Game theory is based. It's a nice thing to see. So we are going to assume it exists unless we say otherwise. And people are infinitely rational, so they always choose the best possible for them given their knowledge. In some models they may not know everything, they may be only aware of something, but given what they're aware of, they're going to be infinitely rational. And of course that's not happens, but it can give you interesting insight, not only in a basic course but also in reality. So of course sometimes it fails, so I'm not saying that's the only thing we need in game theory, but that's an important, models can be very important even under those classical simplifying assumptions. Okay, so now let us go into non-cooperative game theory, which is going to be our first time part of our course. And the first time we're going to see also a bit of an overview of this area of game theory. And from the next set of slides, probably that's going to be the next week, we're going to drastically zoom in to one of the interesting parts of this non-cooperative game theory. So, the model includes agents which freely choose strategies. That's the basic of the model, which strategy an agent chooses. And if the agent knows that he has some utility, he chooses a strategy that will maximize the utility. What exactly the agents assume about the other agents, that's already a question which can be answered in different manners, but the general assumption that agent choose strategy that determines their utility. Sometimes, by the way, in the book you see that the chosen strategy, the strategy profile, so all the set of chosen strategies, but into an outcome which actually provides the utilities. But we are going just to assume that given the strategy profile, agents immediately have some utilities. So if one general does this, the other general does that, then one general has that utility, the other general has that utility. So the game models the setting that people, or in general participants, which can be companies, animals, whoever, behave in certain ways, and based on the outcomes of the total strategy profile, they get some utilities. And an instance of playing such a game is called the play. So the game, instead of players, the strategies, the utility description, all that, the description of reality, so to speak, the rules of the game. And one time we run it, that's called the play. So I choose this, you choose that, that's the play. Another day we do something else, that's another play. Now, the main models here are the normal form game and the extensive form game. Normal form game is also called strategic form game. And normal form game is the following. So it abstractly models interaction of agents. So without going into the details what exactly the agent thinks, just an agent has some strategy which can encode a complicated contingency plan of what the agent does if the other agent does something else. But the model just assumes which strategies there are and what are the utilities that each of the agents obtains given each strategy profile. So that's an abstract model of interaction which allows us to concentrate on the things which basically derive from the general setting of agents, behaviors, and interaction. The general setting. In order to study the details, the exact details, what the one can think from what the other did and so on, that's extensive form. But now we are in the normal form. So you may choose any strategy from your set of strategies, and that strategy is completely independent on what the others do. The question is what you would get, so you can effectively prevent the player from choosing some strategy by giving a very bad utility in this model, but theoretically you may choose any strategy. And as I said, I don't assume that strategies are simple. A strategy can be called A, but it can represent a very complicated set of rules. It's simply that this model concentrates on an abstraction level, and that abstraction level assumes the strategies are just, that's a strategy. Formally, there is a set of players N. We assume it's finite. A set of strategies, a Cartesian product, a so-called direct product of the strategies of agents, and a set of utilities. A utility is a function from this direct product of set of strategies, so which gives for any strategy tuple a real number which expresses how much that agent wants that thing. The utility function like we described earlier. And we assume always that unless somehow I tell you now we assume something else, but probably we won't have it. We always assume n is finite, and if we also assume that S is finite, so all the strategy sets are finite, then we call the game finite. we can work with other games. If the game allows an agent to choose a real number between 0 and 1, that's definitely an infinite game. But often the games are finite, so you can choose one of the moves in a card game, whatever. So that's the definition of normal form game. Now let us talk about an interesting topic, which is an introduction to what agents want to do, and when we're going to talk about Nash equilibrium later in later lessons, we are going to use it. So that's going to be a very simple introduction. So first of all, define a so-called best response of agent I to strategies of the other agent. The strategies of the other agent, are denoted as S minus I, and the best response of agent I to the strategies of the other agent is the set. It can be empty set, it can be the set of all the strategies of SI. It's the set of all the strategies in the set of that agent's strategies, such as the utility that agent derives from playing as that strategy is at least as high as that agent would get from playing any other strategy against S minus I. So it's a best response. Now, it does not always exist. In finite cases, you always can find the maximum, but it may be that in an infinite case, if there is some discontinuity and lack of compactness or something like that, it does not have to be that we have a maximum. A set may have no maximum. So it's not like in all mathematically possible games any agent always has a best response. No. Now when you often do, in finite games for example, you always do, you can define a so-called best response dynamic. So an assumption of how the agents play. So they start by the strategy profile, so strategies of all the agents, at time 1. That's else in parentheses 1. Now, let all the agents simultaneously write down what are their best responses to this S1, so to the strategy tuples of other agents in S1, and simultaneously play. So that's going to determine S2, time 2, and so on. Then every agent responds to what happens in S2 and so on. So they do it, they work like that. So let's say that you have two people, and I am seeing what the other businessman does, what the other person does, and I adjust my behavior to the best that he did the day before, and he does the same, and next day my behavior may already be not optimal to what he does now, and so on and so forth. So this may at some point become constant, this may sometimes converge, it may not converge, it can cycle, there are many options. But when the best response exists, there are many, by the way, best response dynamics in general, because when you have when the set of best responses has more than one option, you can take any option. So this definition allows for many options. Another dynamics, which is when they choose one player at a time. So first, all the players don't move, and then player 1 chooses her best response to what the others do. Then let's say round robin, player 2 chooses the best response to what now the others do, taking into account that player 1 has changed what she did. then take into account the change in player 1 strategy, in player 2 strategy, player 3 changes her strategy to be a best response, maybe one of many, to what others do, and so on. And they act like that infinitely long. That's also a definition of a sequence. We are going usually to, if we talk about that, we're going to work with the first kind of best response, unless say otherwise. And I said it can be an empty set, so it's not always well defined, but if it's not an empty set ever, then we have this sequence defined. And now let us look at some examples of normal form games. So these are very classical games you may have heard about before. They're simple, but they definitely capture some important interactions. So one is called prisoner's dilemma. So when you have two people, the story is like that. You have two people, they have committed a crime. Now they have been caught and put into separate cells, and they are asked, would you like to cooperate with the investigator and to incriminate yourself and your neighbor? So it's a symmetric situation. For the player whose choices are different roles, we call him the role player. This is, by the way, a matrix way to write players, to write such games. It's very useful, very inconvenient when you have two players. If there are more players, you would need a 3-dimensional, 4-dimensional, so on matrix. So the number of dimensions which you need is exactly the number of players. So it's only convenient when you have two players, but then one player whose strategies denote the roles is called the role player, and the other player is called the column player. So here player 1 is a role player. The player can cooperate with the investigation, and then the player, you know what? Let me change this. I think I need to change this. 1 second. Okay, so now I've changed. Now I've changed what's going on, because there can be several stories which give rise to the same strategic situation. So the first story, look at the left matrix. It's the first story. So the two prisoners have committed a crime, and then they can either remain silent, and then here I don't write what they get, I write the cost. So it's the opposite of utility. They want to minimize that. They get 1 year in prison, because if they're both silent, the investigator can only, the prosecutor can only prove a minor offense. They only get 1 year in prison each. Now, if they both talk, however, then they can be indeed proven guilty to a much more serious offense and get 3 years in prison. However, if I talk and the other guy is silent, then I don't get anything, because I can make this agreement, this investigation. I tell them everything, and then the other guy goes in for 5 years, and I get for free. I get 0. And symmetrical if I am silent and the other guy talks. So in this situation, regardless let's say again it's symmetric, but let's look at the thought of the role player. Regardless what the other player does, it's always better for me to do what? Maybe you want to stop the video and think. It's always better for me to talk. Because if the other guy is silent, if I talk, I will get 0, which is better than 1, because I want to minimize, that's the number of years in prison, remember? And if the other guy talks, it's better for me to talk, because that way I will get 3, which is not as many as 5. So we're going to formally study this in the next lecture, but it's so-called dominant strategy. It's strictly better for me to talk regardless what the other person does. So it's reasonable to assume that I will talk regardless what the other person does, regardless what I know, what they do. So I don't assume I know, I assume they all can give their strategies independently. But it's always better for me to talk. And the same for the other guy. So eventually we are both probably going to talk and get 3 years in prison. So the only reasonable result here is that they both talk and get 3 years in prison, which is worse for both of them from the situation when they were both if they were both silent. But simply that if they had both been silent, that's not stable, that's not strategically viable. That's example that when you think about your own good, it's not necessarily that you make it better for all of you, or even for yourself eventually. So it can be that the direction is such that you need some means of coordination. Otherwise, you are going to be screwed like here. Now, we're usually going to talk about another form of the same game strategically. So we call talking defecting because they don't cooperate with one another. They cooperate with the investigator, but the players are the prisoners, so they don't cooperate with one another, they defect. And being silent is cooperating with one another. And if you look at the utilities, what they want to get rather than on the cost, what they want to minimize, then a possible way to write this, that's this one. So, if you both defect, you both get smaller utility. Again, it's the opposite of this one. Smaller utility. If you both cooperate, it's much better for you. But it's not stable because it's always better for you for everyone to defect, regardless what the other person does. And there can be other stories which are modeled that way. For example, 2 people are doing some business without the option to actually write a contract or something. Of course, it's better than that you cooperate in the business, then you get 3 rather than you both defect. But if the other guy cooperates and does all the work and you ride with the money, then you get 5 and the other guy that gets nothing. That's so-called the tragedy of commons. So when you cannot enforce cooperation, it's sometimes, like in this case, better for you to think about yourself and screw the others. And since it's better for everyone, then unless people have some other reasons to behave well, which they often do, people are going to behave badly. In experience, people often do behave differently. And in life, you know, people don't always behave badly, because in reality, people don't usually have only such pairs. Usually, people have other motivations, such as being nice. Sometimes interactions are repeated and so on. But formally, if they only care about that, regardless anything else, it's reasonable to predict that they are both going to defect, or in the language of the previous story, they're both going to talk with the investigator, and both are going to be worse off than they would be if they had cooperated, or in the language of the previous model, if they had been silent. So that's the famous prisoner's dilemma, which is, as I said, a case for 2 players of the more general model, which I think we are going to see next lecture on the tutorial, which is called the tragedy of commons. Okay, so let us now go to another classical model used actually in evolutionary biology. I do recommend reading, for example, the famous book by Richard Dawkins, The Selfish Gene, and he describes that on a high level, but still interestingly, very interestingly, how Maynard Smith, a famous evolutionary biologist, used this model to model how animals choose the way of their behavior. So the model is simple. Two animals want to get something. For example, you have two pigs who want to get an acorn they both like. So they can be hawkish or dovish. Now, being hawkish means that they fight and they actually then wound each other, so they are both in negative utility. We assume he has symmetric forces, symmetric chances to be wounded. Now, on the other hand, they can both be dovish, and of course, being like a dove, it's an allegory to being peaceful, regardless that the real doves are not necessarily peaceful. So, if they're peaceful, they just divide this between two of them, they get half of each. Now, if one of them is dovish, another one is hawkish, then the dove gets nothing and the hawk gets everything. So, if the role player is a dove, and the column player is a hawk, then the column player gets 1 and the row player gets 0. And symmetrically, if the row player is a hawk and the column player is a dove. It's not always better to be a hawk if with a higher chance that the other person is a hawk. So, in the example of animals paired randomly against one another in some population, when they can only approximately size up the other animal's strength, it's not always to fight, and that actually explains why evolutionary forces do not always favor aggressive individuals, because it's actually dangerous. Not because people are nice. Well, nice is something else which has developed for other reasons, but on this basic level, it's not profitable for you. Only on this model, you can see it's not always profitable for you to be aggressive. Sometimes it's profitable for you to be mild. And we are going to talk about the evolutionary processes a bit more in the later part of the course. Okay, another example. So now I need to. It's good that I see this notification. Let's consider the dynamics of best response. I remind you that assume that everyone chooses the best response to what should others do. So, for example, let's look at the prisoner's dilemma in the utility formulation, which is a classical, so when you can cooperate a defect. Let's assume that the profile which they begin is this one. So the best response for the role player, you may want to stop the video and think of yourself. Regardless the column player's action, the best response for the role player is always to defect. So the role player does not change what she does. The column player, however, changes what she does. Because again, for her, the best response is always to defect, and the game is very simple. So they now move, the next profile is going to be defect. And that's where they stay. And actually, from any profile they move to defect, and that's where they stay. In this game it's simple. Now in the case of hawk dove, it's actually different. So if they were hawk, both were hawks, they both suffered, and then given that the other person is hawk, it's the best for me to be dove. So in the next stage, if they both begin as hawks, they are both going to be doves. So this guy is dove, this guy is dove. No, that's not. They're going to go here. Now what's going to happen in the next stage? What is the best thing against a dove? To be a hawk. Because if you are a hawk against a dove, you get 1. Comparatively more compared to the half you get if you are a dove against a dove. So then you move to be both hawks, and that's how they alternate between hawk and dove. That's interesting, isn't it? Now, so we know that if they start as hawks, they're going to infinitely longly alternate. The same if they start as doves. Now, if one is a dove and another one is a hawk, then the guy who is a dove will say, okay, it's better for me to stay a dove. I don't want to be hawk against hawk, because being a dove against a hawk, I'm getting 0. Being a hawk against that hawk would give me the -2. And the guy who is a hawk also will stay, because being a hawk against a dove is 1, which is better, strictly better than becoming a dove against a dove and getting only half. So no matter who is the hawk and who is the dove, but if one is one and the other one is another one, they're going to actually be stable. So if they start here, here, or here, they're going to be stable. Okay. Other classical examples we are going to see on the next lecture.